what keeps this topic interesting, intriguing, and stimulating, despite centuries of research on that topic. Now, in the title, I mentioned dual continuum representation, and what I didn't mention, I did mention actually, fractures as well. So why are we looking at fractures? First, what are fractures? Fractures are disrupting interruptions in our rock that have different properties and are potentially connected over long length scales. And they actually play a major part of, with respect to, did something change here? With respect to the remaining oil reservoirs, because recovery and recovery estimation for naturally fractured reservoirs is a challenge. So they also pose a good potential for geothermal energy, since they typically provide a high permeability and large contact area. And they also provide a potential for geological carbon storage. And last but not least, they are utterly important also for tight reservoirs, because they provide the access to the pore space. Now, what is the challenge? I'm presenting here results from 3 simulations for a specific fracture network. And the only difference in these fracture networks is the aperture. And in the top left, we see an aperture of 100th of a millimeter, and in the top right, an aperture of the fractures of 300ths of a millimeter, and then at the bottom we see 1 millimeter aperture. And we see in these figures a flow from left to right. And if you now picture that this color coding, the red could be some sort of contaminant, and we are interested in how fast does this contaminant propagate through our porous medium. Now, we have a very subtle change in the aperture of the fractures, but we see completely different flow patterns. And if we now have a drinking water reservoir to the right, we might be very well interested how quick our contaminant reaches the right end. And the snapshots on the top are after 150 days both, and at the bottom it's even only after 30 days. So the flow pattern that we observe here is highly sensitive to the aperture. A different application is if we think that blue is oil and red is water. That might be a bit counterintuitive, but I guess you are intellectually flexible enough to make that little exercise. Then we inject water to displace the oil, and we can think of a producer at the right. And then we see that if we have very small apertures, the water propagates in a pretty stable front, and we can sweep nicely the oil out. While if we look at the larger aperture, the water will just break through the fracture network, and we will leave most of the oil in the underground. So that's why fractures pose a significant challenge to the modeling. And let me add to that, this has been simulations on a cluster of high-performance computers, and the simulations been running for quite a while because of the required high resolution of to map the fracture network. So this is absolutely not a practical approach if we are talking about industrial applications. So we need to simplify that problem to capture the essential dynamics and in order to plan engineering strategies on whatever application we are interested in here. And of course, this problem has been identified for a while. And even 50 years ago, people started conceptualizing a fractured porous medium. So instead of going into the details of the physical geometry, we started idealizing that in sort of a sugar cube model where we have regular void space of fractures that are separating individual matrix blocks. And if we now want to model that, use this conceptual representation to model the fracture pattern, we identify a medium of fractures and a medium of matrices, and then we will let these two mediums interact through transferring mass depending on the physical processes at hand. And now, looking at the equations, we will have the standard mass conservation equation, and we will add a transfer term here that now represents all the interesting physics that make fluids pass from the fractures into the matrix and vice versa. So in these transfer concepts, the transfer function represents the exchange between the fracture continuum and the matrix continuum. It should account for different exchange processes. It should account for the contact area between the fracture continuum and the matrix continuum. And it should take continuum variables as arguments. And then we can formulate a typical shape that allows us for a transfer that is proportional to some potential difference. Now, what are the typical processes that we are looking at? In the oil and gas industry, this is typically spontaneous imbibition, where capillary forces soak the water into the matrix. It is fluid compression, so that we have different pressures in the fracture and the matrix. We have gravity displacement, and we have molecular diffusion. And of course, this has been around for a while, but we are still not fully able to capture all the physics because the phenomena are heavily nonlinear. So the question is, what is a proper first order representation of the processes? Can we isolate individual processes? In other words, is the system behaving despite being heavily nonlinear, linearly in certain aspects? And then the question is when to use which representation. Do we have proper scale separation? What about the mysterious shape factors that are occurring in typical modeling approaches? And can we be predictive rather than having a fetch factor for history matching? And then going further and further and including more and more physical and chemical processes. So now that I've presented a general idea of dual porosity models, I want to explore how we can use this simple dual porosity model to assess whether there's any CO2 storage potential in naturally fractured reservoirs. When we look at CO2 storage and take this cartoon representation, we will have the CO2 first quickly residing in the fracture network. And because of the highly conductive fractures. And the two main questions pop up. Do we actually get the CO2 into the matrix? Because that's where most of the volume sits. So that's where we can achieve safe CO2 storage. And can we control the migration of the CO2 plume? So now we can go back to our conceptual representation, and we are now facing the challenge: how can we formulate appropriate transfer functions that represent the processes that deal with the fracture matrix transfer? And we've been exploring the use of analytical solutions and revise our understanding of the matrix fracture transfers accordingly. And this is again where mathematics this is a perfect example where mathematics can help us in achieving a substantial improvement in the understanding of the overall system and hence in engineering design. Does it really matter? So I'm showing here two different simulation runs. With on the left, you see a simulation run with our new model that I will introduce on the next few slides. And to the right, you'll see the state-of-the-art of that is used in commercial simulators, for example. In the top line, you see in color-coded the amount of CO2 in the fractures, and at the bottom you see color-coded again, yellow representing the CO2 in the matrix rock. And these are snapshots after 40 years of injection, and then I have some snapshots after 120 years of injection. And the question now is, does that actually matter? Well, we see the spread of the plume is not so substantially different. However, the amount of CO2 that we were able to store in the matrix differs by 0.4 megaton of CO2 per year. Now, does that matter? Well, it does matter in that context because overall we are injecting 1 megaton per year. So this is a difference in 40%. So how do we get, what physical process brings the CO2 into the matrix? And well, CO2, even in its supercritical state that is usually used to inject, when injected in a formation for storage, is substantially lighter than brine. So we get a buoyant drive, and that will induce a displacement of the resident brine in the matrix and displace or lead to a displacement of the CO2 of the brine in the matrix with CO2. And then at some point we will stop the injection, and then buoyancy brings CO2 to the top of the imbibition and to the top of the reservoir, and re-imbibition may happen. So this is then a different physical process. So with this idealization, we can run simulations on this simple conceptual representation and see what conventional models provide us in comparison to what we actually see. And we see a substantial difference here. Note that, so this is the amount of CO2 stored in the matrix, and this is a logarithmic scaling of the time. So we have a mismatch of several hundred days, and that's reflecting in the substantial difference that we've seen in the previous simulation run. And I think with respect to time, I'm going a little bit quicker here. So how did we approach this challenge? So we observed that the dynamics that we are looking at here is essentially one-dimensional. So we can simplify our equation and just look at a one-dimensional fractional flow equation. And I hope that at least the students here that attended the reservoir simulation course the last 2 weeks are very familiar with this formulation. And then we can use this formulation to estimate orders of magnitudes for the time scale. And by approximating the nonlinear terms through characteristic values. And from that, we can actually pretty quickly get a reasonable order of magnitude estimate and can put that into a simple first order displacement model. And we use that to compare for realistic parameters for CO2 storage formations. And on the left, you see a comparison of the performance. On the x-axis, you see the time it takes to displace the CO2 into, or displace the brine in the matrix, and at the y-axis you see the amount stored in the matrix, and then the circles, so the points in this figure are giving you obviously a time value and a storage value, and the inner circles are the error of our new models compared to explicit simulations, and the largest circle are representing the error from conventional models. And we see a substantial improvement over the whole context, over the whole phase space. And in the right, you see explicit representation, again, time as x-axis and normalized CO2 volume as y-axis. And the solid lines are our reference solution, the dashed lines are our model, and the dotted and dash dotted curves are state-of-the-art from the literature, and color-coded are different parameters. So how much more time do I have, Chairman? Five minutes? Okay, let me go then and apply this to a sort of realistic structure and see whether it matters in a quantitative setting. So we tend to want to store CO2 in anticline structures with an impermeable layer on top, so that the CO2 doesn't migrate up again to the surface. And we know that from oil and gas, that's where we tend to find hydrocarbons. And we can then start injecting CO2 in the center of our anticline and see what happens if we suddenly observe that even though we thought the reservoir is not fractured, there might be fracture present, and whether that is any detrimental for our CO2 storage project. And in the left bottom, you see the CO2 distribution color-coded for the unfractured case. And then on the top, we see the CO2 plume in the fractures, and we see the CO2 plume in the matrix. And what we immediately observe is that the CO2 fills the anticline much more evenly because the fractures are way more permeable than the rock matrix, and hence it moves much faster up in the reservoir and spreads over the lateral. Now that means that the CO2 can actually escape here at the edges. And this is something that we want to avoid, because that means we lose control over CO2, and that might lead to contamination of neighboring potable aquifers or detrimental effects if we have a gas reservoir next to it. And what we see here is the mass of CO2 in our system, illustrated over time. And we see in blue the unfractured model. So we inject for 1,000 days and stop injecting then. And then in the fractured case, we can now look at the amount of CO2 in the system. That's our red curve, and we can see the amount of CO2 in our matrix. That's the dashed curve, and in our fracture system, that's the lower curve here. And we see that CO2 starts to migrate out of our fractured reservoir. And then we can again take a look at the parameters that are generally known for different formations and see whether it matters significantly or not. And we can identify situations when the transfer between fracture and matrix is rather fast because the permeability is rather high. And in these cases, we see that we don't lose too much storage. But then if it's if the transfer is slower, then we lose some storage. So to conclude, I hope I presented to you that multi-phase flow in porous media is an exciting and relevant topic for many applications with many open scientific questions. I mentioned that we want to make models as simple as possible, but not simpler. I illustrated that with the dual porosity representation, where we've seen that you can oversimplify and then be off by several orders of magnitude, but the moment you start thinking about the physics and identifying symmetries, mathematical structures, you can actually obtain simplified models that capture reality reasonably well. Fractures are a challenge, and dual continuum formulations, even though 50 years old, they are still relevant for many applications. And last, I've discussed geological storage of CO2. That's an opportunity to mitigate or slow down climate change. And I've mentioned the last item before, simple models with the right physics can save us a lot of CPU hours. And with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Okay, so thanks so much for the lecture. Questions, please. Any questions?
Richard? Oh, sorry.
Thank you very much. Please, I would like to find out if this model can be used to quantify oil in place. That is your model, whether it could be used to quantify the amount of oil in place, or petroleum in place?
Well, I need to probably go into a little bit of details of the terminology here. So the oil in place is an input parameter for this model. But the recoverable oil that is in place, that heavily depends on the physical processes. And for that, we can use this model.
Thank you. I came in late, but I think, let me put the question this way. I know carbon dioxide is able to react with brine.
Yes, it dissolves in brine.
Yes. So how does your equation explain that transition?
This dissolution is not accounted for in this first order model, and if we go through a timescale estimate, this dissolution tends to happen on a timescale of decades to centuries, while we are looking here at the first initial displacement on a timescale of years. And it is like we can incorporate dissolution as well in that setting. That has been studied heavily for unfractured CO2 storage in unfractured reservoirs. Following the same protocol that has been used for the investigation in unfractured reservoirs can be mapped onto our model, and we then have to trace like how do the physical processes change once we have fractures and matrix present. Dissolution fingers, so there tends to be some instabilities because brine saturated in CO2 tends to be denser than unsaturated brine. So then the question is, do these what's the width of these characteristic fingers? How do they compare to the matrix size? Yeah, interesting research questions.
Okay, I must say that I really love your presentation. Please, can you go back to the slide 28? I have 28.
28.
I think 28.
Yeah, I understood 20.
Yeah, when you mentioned the models, what you're going to look at, you mentioned gravitational, you looked at viscosity into the computation of your model. But I was thinking, did you also look at the stress perturbations because structures are
so in this model approach, we assume that the forces exerted by the fluids are minor compared to anything coming from the stress of the overburden, and assume that the rock is rigid and doesn't deform. However, I have a few students currently expanding our simulation capabilities to account for stress response as well, and that's again an exciting research topic.
Thank you.
Thank you for your presentation. I want to know what causes fractures in porous media.
Difference in stress. So in order to understand how fractures form, we cannot ignore the stress your predecessor in the question was asking towards too.
Please,
Please, may I know what is actually causing the phase change? The phase change to...
We are not looking at a phase change here. So
Okay.
we have fixed states. So the CO2 is one phase, and the brine is another phase. And the CO2 can, or like at certain depths, is in its supercritical state. If it migrates higher up, then we might see a phase change that it turns into gas, but that's not looked at in this model here.
Okay. And again, I want to know how you incorporated the Darcy equation into, because of the porous medium. You are looking
Yes.
at.
Here we are.
Okay.
Does this answer your question?
Yeah. Thank you.
Okay, that's the final one.
All right, thank you. I want to know why dual porosity but not multi, and also does the model capture the dynamics in the transfer between the matrix and the fracture?
I didn't get the first part of your question. Could you repeat that, please?
Why dual porosity but not multi?
Because you have to start somewhere. And that's the honest question, but then you can start reasoning for that. And if the fractures are rather monodisperse, having more or less the same aperture, and porous medium is rather homogeneous, say a nice sandstone, then that's actually a proper representation. However, if you go to more complicated rocks, then indeed we might have to look at multiple continua, and this is also part of the research questions that we address in my group. When to represent how many continua do we need? Can we get along with simple upscaling, homogenization, or do we have to represent the different continua separately? Now, your second question was, do we represent the transfer of in between fracture and matrix?
Yeah.
Yes, we do. That's exactly the challenge and I've presented one special case here for when buoyancy displaces the CO2, and we used a 1D representation to identify characteristic timescales and then feed that into a first order transfer model.
I think that's the.
Richard should probably ask, because he raised his arm at the very beginning.
Okay, go ahead.
Yes, my question is, since you are taking advantage of the porosity of the media under consideration, and there could be changes in the properties of the other media you are considering, say the brine, do you anticipate a situation where there could be leakages? Because we didn't see that. And how do you mitigate that one if there's going to be situations like that?
The big challenge here is to answer that in a short sentence. So leakage of CO2 is indeed one of the main concerns, and there are research endeavors across the world that try to understand more detailed what could induce leakage and what could prevent it. In general, it's definitely possible to not have leakage because we see hydrocarbon reservoirs in the subsurface. So if they would be leaking, they wouldn't be there. So the short answer, it depends. So you need a rock that is that has a low permeability and that has a high capillary entry pressure in order to keep the buoyant CO2 below. And that would prevent leakage, yes.
Okay, the last one. You raise your hand.
Yeah. Okay. In your equations, the two equations you used to answer a question from this side.
Yes.
Can you go to them, please? Okay, in the second term, I see you having density with G. I believe it's gravity.
Yes.
Don't you have a change in height? Or how are you using gravity without change in height?
I have to smile at your question because I used a slightly different notation in the class. The gravity here is a vector that points in a direction, and then the buoyancy comes into play by looking at the two equations for the two phases. But we can discuss that in the break, and I try to rectify my inconsistency in notation.
Okay, thank you.
Okay, thank you very much. The next speaker is Kofi Ohimi Chi Prempe. He will be presenting Ombudsman transformation approach to simulate a two-phase radial diffusivity model for tight oil reservoirs. Okay, shall we welcome Mr. Prempe?
Good morning, everyone. And, my voice could be quite low, so pardon me if you can't hear me very well. So I'm here to make a presentation on a Boltzmann transformation approach to simulate a two-phase radial diffusivity model for unconventional tight reservoirs. And I wish to acknowledge Professor I.K. Donchi and Dr. Peter Yerinchi and our recent Dr. Nana Kina for their input in my work. Sorry. Wow, okay. I'll just use the... Thank you. Okay. So this would be the outline of my presentation from introduction right to the references. And before I start, I would like to give a short introduction and overview of exactly what motivated this work. The decline of conventional hydrocarbons, as we know it, is on a global long-term decline, as indicated by Contd in 2012. And the plateau of these oils require for us to now look at how to explore unconventional reservoirs that occur in the world. The world is approaching the end of easily accessible hydrocarbons, and it is worthwhile to actually look at how to move on to find other sources of hydrocarbons. Now, unconventional resources, as we know, it has a lot of definitions in the world. Several researchers tend to define it based on a threshold by saying that all reservoirs with a lower permeability of less than 0.1 millidarcy can be classified as unconventional. Apart from that, other researchers try to explain it using the geological structure, whether there is a presence of a trap or not, or whether the basin that it exists in is either continuous or centered. But I prefer to rather use the definition of Contd again, where he tries to define unconventional reservoirs based on the permeability-viscosity ratio of the system itself. In that case, you tend to have a more mathematical definition for unconventional reservoirs without relying on just qualitative definitions. Now, why unconventional reservoirs are necessary today is because of the vast amount of unconventional reservoirs in the world currently. Because of their inability to access them easily, we tend to ignore them. But I think now, with the recent technologies we have, we can pursue their exploration. So if you can see the technically recoverable volumes of petroleum that are still classified as tight oil or unconventional reservoirs is quite huge. So we know that reservoir simulation requires the use of PDs, and these flow simulations predict behaviors within the reservoir, and these are quite complex and very hard to study. Apart from that, the complexities associated with the PDs that describe the flow simulations are quite difficult for reservoir simulators to find immediate solutions. So I think it is worthwhile to find alternative solutions that would help us find solutions to the problem without losing vital information of the system. So what alternative solution did we look at? This study tried to use the Boltzmann transformation approach to try and simulate the flow problem, just to help us convert the complex PDEs into simple ODEs, but I mean complex partial differential equations to simple ordinary differential equations that could be easily solved. Now, these are some of the motivations that have already been done in literature. The first person who initiated this was Boltzmann in 1894, where he used the similarity variable to help in his work on the fixed second law to convert it into ordinary differential equations before solving. Another group, that is the Karl's law and the Jaka, in 1959 also adopted this approach to find analytical solutions to the heat conduction problem. And to mention a few, this is just the main focus of the work. This was done by Tabatabe and Poladi in 2016, where they used a similarity variable to solve for a multi-phase linear system in tight oil reservoirs. But this particular case in this work, we looked at a radial system. So the mathematical formulation of the whole model was based on these two equations. The first one is modeling the flow of oil within the system. The second equation is modeling the flow of gas within the system. But here, I want to bring us to the notice of something really special here. It is normally known for tight oil reservoirs to have gases dissolved in solutions, and they tend to evolve once production resumes, or they evolve once they reach a thermodynamic property called bubble point pressure. So here, to accommodate for that, we see equations that correlate with gases in solutions and gases that evolve out of solutions once the process is initiated. And I believe these parameters can easily be comprehended. So once these equations are obtained, it's best to also re-parameter, as in re-evaluate them into a form of a PD that can be easily evaluated. So here I use these parameters, alpha, beta, to just make a real representation of the whole equation into a simplified form given by equation 3 and equation 4. So once this is done, we now adopt our Boltzmann transform. What it simply does is it combines our independent variables, which is the radius in the spatial domain and the time, into the Boltzmann variable. And once you're able to do this combination of variables, you're able to now reformulate your original PDs into ODEs given by equation 6 and equation 7. So we now have our ODEs established by the Boltzmann transformation. We need to now take it through a process of simulation to see how well it works with the, in conjunction with the PD. So we adopt this simulation data looking at a reservoir of size 800 meters and 50 meters thick, and simulating for about 500 days. But the most important feature is the production scenario. We are assuming a constant production of 10,000 kilopascals and a reservoir pressure of 50,000 kilopascals. And just to note, we are using the Corey type relative permeability curves to describe our flow problem. So with coefficients of 2 for both the oil as well as the gas. This is actually based on the work done by Tabata B and his colleague in 2016. So we were able to establish a numerical solution for the PDs given by the diagram as shown. You see that we have pressure distribution from the wall bore from the initial reservoir pressure of 50,000 kilopascals to the near wall bore scenario where we have a constant production of 1,000 kilopascals. Now, once you're able to initiate this pressure distribution, we also have to account for the oil saturation distribution within the system. And here we realize that initially we considered that the system is completely saturated with oil with a saturation of 1. But as soon as we start our production, which goes beyond our bubble point pressure of 50,000, gases start to evolve. So it's invariably, we expect that the saturation of oil should decline to allow for the evolution of gases out of the solution. Therefore, you see a decline of saturation from 1 to 0.7. At the same time, we also expect an increase in the gas saturation from its initial stages of 0 up to a value of around 0.3 near the wall bore. So once you're able to do this, we know that the recombination of the solutions from the partial differential equations can be remerged into a single curve once we use it against the Boltzmann variable. And here we compare the solution from the Boltzmann approach to the numerical approach, and we see a very good mapping between the pressure distribution from the Boltzmann approach as well as the numerical approach. Then we also take a look at the distribution of the oil saturation as well as the gas saturation, comparing both the numerical and the Boltzmann approach, and we realize that both of them are reasonably given a good fit. Then the last investigation that we also undertook was to look at the gas-oil saturation profile of the system, just to see how well the Boltzmann approach was able to mimic the exact nature of the reservoir, and we recorded a constant gas-oil saturation as soon as production started of a value of around 1,200. So in conclusion, the Boltzmann facilitated the conversion of the PDs into simple ODEs that helped us calculate it quite easily. Apart from that, we were able to use the similarity approach to offer ourselves a good mapping of the original PDs and to gain an easy solution to the problem. And finally, the gas-oil ratio also tries to conclude that the recombination of fluid samples at the surface is in the ratio, the recombination of fluid samples collected at the surface in the ratio of the gas producing, the gas-oil ratio does not represent the in situ reservoir fluids. What I'm trying to say is because we know that within the reservoir there will be a fluid, the presence of gas and oil, it doesn't necessarily mean that the ratio in which they recombine within the subsurface would be the exact same scenario when they are produced up to the surface. So thank you very much. These are my references. I would now welcome questions.
Okay.
Thank you for your presentation. My question is simple. What is the study area?
I can't see who's asking the question, please.
Oh,
sorry.
Yes. Yeah. I didn't get an idea of where you carried out the study.
Oh, it's in reservoir simulation, petroleum engineering.
Is it a hypothetical situation, or because I was expecting maybe an area where you really carried it out?
Okay, this was an overview actually. It's supposed to give us an insight into how radial systems behave. This was an improvement on the work done by Tabatabe in 2016, in which he looked at a linear producing system. But in a natural sense, if a reservoir is radially perforated, we expect it to take a radial pattern into the wall. Well, for that reason, I had to look at the radial system of propagation.
So my point is it a hypothetical situation?
Exactly.
Okay.
Okay, thank you for your presentation. And thank you, Dr. MC. If I look at your work, you've done extremely well. But in case the university wants to employ you, where do you fit?
Naturally, personally, I actually fit in the petroleum engineering department, but the whole, I don't know whether you'll allow me to give you a whole. I'm a petroleum engineer from BSc, okay. And I figured reservoir simulation needed a quite amount of mathematics. You needed to know how to model, how to go about solving the problem. So I decided to dive a little back into math, but I'm hoping to go back into engineering, hopefully.
Okay. Thank you.
Chairman, one question.
That was a technical question.
I overheard you saying that what you did was hypothetical. Yeah. Did you use any data at all in your work?
Yes.
What did the data come from?
The data came from the work from Tabatabe, and
where did he get the data from?
He did. His data was from experimental pressure. And, okay, let me say he had lab data, lab results. But the reason why I said it was hypothetical was the field was not. I think he was rather referring to engineering terms, whether the field is a physical field or just a so-called hypothetical field. That's why I said, well, it is hypothetical.
No, I'm saying that the data that the paper that you reviewed used.
Yes.
And didn't take it from some physical place. The experimental data. He took some experimental work and then he did the work on it.
Yes.
Then you use that same data to update your work. So
yes.
How is that hypothetical? So it's not, isn't it?
Yes, I think that's a good piece. Yes,
thank you.
So I've seen two equations on the, like you were modeling the flow of gas and the flow of oil.
Yes.
Doesn't that introduce two time scales of diffusion, and are you able to represent these two time scales in one Boltzmann transform?
Well, I'm assuming that the initial saturation, the oil is completely saturated with oil. So I'm assuming 1 time scale. And the thing is, once I initiate production, I have both oil and gases evolving out of the solution. So if I do it on different time scales, it would seem almost as though I take out that instant evolution of gases out of solution.
So are you saying the oil is not flowing but only evaporating?
No, the oil and the gas is flowing, but the boundary conditions I gave it, the 50,000 reservoir pressure is also the same bubble point pressure within the system. The bubble point pressure is where I expect the reservoir to start producing the gas. So initially, if it's under a saturation of 1 and I initiate a production at 1,000 kilopascals, then I should expect the instant evolution of gases out of solution.
Thank you for the presentation. I was a little bit disappointed that I couldn't see Archie, or Archie's equation from your background, because Archie looked at more or less geological constraints within the system. Maybe you may want to go back and look at that, because the geology plays extremely crucial role in this simulation. So I suggest you want to look at, because every when you want to characterize any formations, of course, the geology plays the crucial role. So I'll suggest that you want to look into it again and factor it into your model. Thank you.
Absolutely. Yeah. Sorry.
One here first. I'll take the last one because of time.
We know for reservoir simulation, we expect that as we produce the pressure in the I'm saying we know for reservoir simulation, as we continue producing oil, like as time passes, we expect that the pressure in there will reduce.
Yes.
Thereby, there will be some kind of, there is a possibility of formation of gas in the system. So I'm asking, there is in light oil production, sometimes there's what we call the gas cap drive.
Yes.
Does it also happen in this scenario?
Well, in this scenario, we didn't look at a scenario in which we have a gas cap drive. We are trying to see that, sorry if I didn't mention the assumptions, I think that's where the, some of the assumptions that were considered is here, the well is centrally placed, and the full thickness of the reservoir, which was considered as 50, has been fully perforated. So we expect fluids to move through the entire height that has been specified. That's what, so here, even if you say that you place your perforations only within the oil zone and you have a gas cap above it to move it, it won't be reflected here because we expect that our entire P thickness has been perforated. So the other assumptions, we are incorporating Darcy's law. We are also assuming that the reservoir has no source term. So I think.
Anyway, thank you. You used the Boltzmann approach to reduce the partial to an ordinary differential equation.
Yes.
I want to know how you solved the resulting ordinary equation.
Yes, I solved it by the a numerical method, that's the finite difference method. But once you have your method to solve, you also need to adopt a scheme, and the scheme that was used here was the IMPES scheme. We call it the implicit pressure, explicit saturation, where once you have this equation, you generate a pressure equation as well as a saturation equation. Then you solve the pressure equation implicitly, then you solve the saturation equation explicitly, then you come up with your solution for pressure and saturation distributions.
Can I know what informed your choice of the numerical method?
The scheme or the method?
The method.
This one will be an honest answer. Finite difference schemes are quite fast in the first place, and I don't want to say they are just widely used. Yeah, let me put it that way. I don't want to be tempted to say the other one. Yes, it could be inefficient, but once you're able to ensure that it is stable, I think it is fair enough. Yes, at the moment, the current research that's done, I wish the other speaker was here. We are trying to look at geomechanics, how it influences it, and we are also trying to move away from using finite difference elements or volumes into adoption of wavelet transformations, which I think someone will be speaking of.
Okay. We'll take a final one before snack. From Daniel Murray. He'll be talking on convergence criterion for a bounded sequence in R. Shall we put our hands together for you?
Yeah, good morning. Yeah. My name is Daniel Marian, and I'm presenting on the topic convergence criterion for a bounded sequence in R. And when you talk about sequence, you know that data is fast changing the facet of the world, and then whichever industry or company wants find himself or herself in it, data is positively impacting on the activities of that organization. And then to a mathematician, a data is a sequence, that's a string of numbers or objects that follows a particular pattern. And then they are very useful in our everyday lives. For example, is the interest portion that we take from loans. Also, the daily or the list of daily maximum temperatures. I use Aperture, for example, because I stayed at that place. And then even in probability theory, the set of numbers generated by if one wants to get a win on, let's say, an nth row is generated by that sequence, that is A and B equal to the probability that the person will lose times raised to the power n minus 1 times the probability that the person can win that through. And then when it goes to the world of real estate, let's say we hire someone to build a pyramidal tower so that we can put our poly tank on it. And then we want the lower bottom to have 17 blocks, and then each block will be 2 blocks fewer than the previous one. So we can generate these sequences, and then we can know the total number of blocks that we will need in that building of the pyramidal tower, and then the number of blocks that will be at the last row. And also in banking, let's say we want to go for we deposit an amount of 1,300 Ghana cedis, offering 27% annual interest, compounded quarterly. And then this money, we generated it, or we deposited it as a seed money for our 8-year-old daughter's university education. So to determine how much the account will value after 17 years, we can also generate these things using a sequence. And then this is how we can generate these sequence. Also, for population management, I also use Mantukwa in Brunafo region. Let's say if you want to find how much the number of people in Mantukwa will grow in the next 5 years, we use the annual rate of 15% to generate, or to find the number, that is the interval and then the total population in the next 5 years. But now the problem statement is that in spite of the numerous application of sequences, a sequence may not serve its limiting value, or may not serve its purpose if the limiting value does not exist. And this also goes in for continuity, differentiability, and then integration. So now, the class of sequence that we are talking about is the bounded sequence. And then a sequence is bounded if it is both bounded above and then bounded below. And then a bounded sequence, a sequence may have more than one bounded value. Let's say the set of natural numbers is bounded by 1. But if the sequence starts from 2, 2 can be the lower bound for the sequence, and then 1 can also be the lower bound for the sequence. But 2 will be the infimum for the sequence, and then 1 will be the 1, and then 2 will be the infimum of the sequence. So now the objective of this research is to find out whether every bounded sequence in R converges. And then if that's not so, then we come out with a permissible criterion for the convergence of a bounded sequence. So as I stated earlier, these two sequences on the screen are bounded, but they do not converge. So now, what makes, or what's the criterion for a bounded sequence to converge? So now the first one is, we look at some lemmas. In mathematics, lemmas are like tools that are used for proving theorems. So we look at this lemma, and then states that if you have a sequence of natural numbers, an increasing sequence, being it monotonic increasing or sweetly increasing, is still an increasing sequence. So if this sequence is increasing, and then it's a set of natural numbers, then that means the sequence, the terms of the sequence, are always greater than or equal to the index of the sequence. And then we prove this one using induction. Also, the first theorem states that if a sequence AN converges in R, then every subsequence of AN also converges to the same limit. That's the uniqueness of limit. If a sequence converges to a limit A, then that means that every subsequence in that sequence will also converge to the same limit. And then this is the proof. If we say a sequence is converging, that means the distance between the sequence and this converging point is very small, that if you compare it by an epsilon is a positive number which is greater than 0, but very small. Say 10 raised to the power minus 10. Okay, it's very small, but it's positive. So if you compare the distance between the sequence and then the limiting point, it's very small, that it's even less than that epsilon that we are talking about. And then Bose-Einstein and Weierstrass also talk about that every convergent sequence, as I said earlier, has a convergent subsequence. So now, then if a sequence is bounded, then it converges if and only if the limit of the infimum of the sequence is equal to the limit of the supremum of the sequence. As I said earlier, when we talk of sequence, we talk of boundedness and then infimum. They are not the same. We can have a sequence being bounded. If it is bounded below, then that means the infimum of the sequence, that is, it will be the greater or the maximum value of the lower bounds. May have many lower bounds, but the infimum is unique. So if the sequence is bounded below, then that means the greater of the lower bounds will be the infimum. And then the supremum is also the least of the upper bounds, being the supremum. So if you're able to get the supremum and then the infimum being equal, then that means that sequence is bounded. And then if a sequence, the supremum of a sequence is, say, A, if you subtract that small epsilon from that number, A, then that A will refuses to be the supremum of that sequence. And that also goes for if the infimum of a sequence is, say, A star, then if we add an epsilon to that A star, then that also ceases to be the infimum of that sequence. Okay. Then theorem 4 states that every bounded sequence, if you have an A that is bounded in R, then it converges if it is monotone. When you talk of monotone sequences are sequences that are either increasing or decreasing. So if a sequence is increasing, then that means it will converge to the sup. And then if a sequence is decreasing, that means it will converge to the inf. And then we can have a strictly increasing sequence. That sequence will also still converge to the sup, and then a strictly decreasing sequence will also still converge to the inf. So now, by conclusion, we, from Bosano-Weierstrass theorem and then the other lemmas and the theorem that we looked at, we've all came to a conclusion that a sequence AN is monotonic, increasing or decreasing. And then if these criterions are being obeyed, then the sequence converges. So now we've looked into a bounded sequence. We have a bounded sequence. So if the bounded sequence obeys any of these conditions, then that means that bounded sequence converges. And then the first one is if it is either monotone, that is, it is monotonic, increasing or decreasing. And then the last one is if the infimum of the sequence is equal to the supremum of the sequence, that is if inf A is equal to sup A. Thank you.
Thank you for the quick way you did it. Questions, please.
Okay, go ahead.
Thank you. I didn't get your name, so I can't use your name, but thank you very much.
His name is Mari Daniel.
Mari Daniel.
Mari, okay. Earlier, when you started, you gave some very interesting examples about real estate and all of that. So I was hoping that after telling us inf and sup and everything, you show us how inf applies in the examples, and you gave your problem statement and everything, but I didn't really see how inf, sup, boundedness, convergence, Bosano-Weierstrass, how all of that come into play in the examples that you gave. Can you please do me that honor? Thank you.
Okay, please, they are all in the big thesis. And then the main purpose of the thesis is to create a convergence criterion for a bounded sequence. Okay, a criterion that a bounded sequence is supposed to follow so that it will converge. Even though we know that sequences are applied in all these areas, but they can't, or they are not useful if they do not converge. So we were trying to see the criterion that this sequence will pass through to converge so that they can be used in these areas.
Yeah, so you ended up telling us that a sequence must be increasing or decreasing. It's one of the things, or probably the limit inf should be equal to the limit sup. Those were the conclusions that you drew.
Yep.
Okay. So, I mean, practically, what you have just said, those two are the criteria. So if I have, like this example you have here right now, and then you talked about some water in a tank or something like that, how can you know that limit inf is equal to limit sup in a water tank?
Okay, let's look at this example. You see, if you, this one, you see the probability theorem. If you find the first term of the sequence, you have 1/6. You see, the second term will be 5/36. You see, it's decreasing. So it obeys the first criterion, that is either that is either decreasing or increasing. So if you have a static sequence like 1, say an being equal to 1 raised to the power n, that sequence is a constant sequence. And then that sequence cannot be used in any of these applications. I don't know if your question is being answered.
Okay. Yeah.
Okay. Thank you. I want to ask, the inf and sup are quite understandable. But I want to know how, since this one has to do with real life situations, when it comes to real life situation, are there any other terminologies that you could use to actually inform us what you really mean by the infant soup, and how do we really appreciate this in a real life? Maybe you have a customer and you have to advise him. I believe the infant soup would be not quite understandable, and if you could use something quite more.
Okay. You see, in this building, we are being bounded. Okay, we are being bounded by the walls of this building. Okay, so that means that we are bounded here, but we can't go beyond. Let's say we are having a conference, we can't go beyond that, the boundary that is surrounding us. So our aim, since when you look at the real number line, it's like a one dimension. So that's why we have the infant. So by here, when you consider or we try to relate it to, let's say in reality, what I can say is that since we are bounded over here, we can't go beyond our boundary. And then this walls within us, that's the place that we are. That serves as our infant and our supremum of, let's say, if this is a reality. You see, the convergence point is like, I talk about the distance. You see, we all came from different places, and then as we are coming, the distance between us closes. So as we are getting close to our limiting point, the distance between us gets closer, like it becomes small, that is even less than the epsilon that I talked about. But if it were to be diverged, if we were to leave here and then go, you see that our distance would be huge. Maybe where I'm staying from is different from where you are staying from. The distance will be huge, but as we've all converged here, the distance is really, really small.
Okay, so that will be the right time to thank you very much. So once again, we want to thank you for this morning session. We'll take 50 minutes snack break. Please, let's keep to the time. 15 minutes. So thank you.
Yeah, but look at me, oh. Look at me. Come on. Swing your handkerchief in the air. Why not? Why not? Ay, ay, ay. Come on, closer. Ha, 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 ha. Good God. Hey, everybody look and see what the Lord has done for me. Everybody look. Come on. And see what the Lord has done for me. Everybody look away. You will see what God is doing. Everybody look. Why not? And see what the Lord has done for me. Everybody look. You will see what God is doing. Everybody look and see. Come on. Why not? Everybody look at me and tell me what you see. Come on. Come on. God's goodness and mercy are following me. I don't know about you. He has turned my morning, come on, into dancing. He gave me a brand new song. Swing your handkerchief in the air. Everybody look and see what the Lord has done for me. Everybody look and see what the Lord has done for me. Everybody look away. You will see what God is doing. Everybody look and see what the Lord has done for me. Everybody look, you will see what God is doing. Everybody look and see. Hallelujah, hallelujah. Push your hands up. Push your hands up. Hallelujah, 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 hallelujah. Cause I said, glory, 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 glory. Come on now, ta ta pa 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 da pa 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 sa pa pa da. Swing your handkerchief, good God. Hey, you come to celebrate. You come to jubilate. You come to celebrate. You come to jubilate. You come to jubilate. You come to celebrate. He got me one time, oh, for my life over you. He did not say my whole life, don't get me at all. I'm not getting lucky, oh. I don't get you money. No food to eat. No clothes to wear. I don't pray to my God. Oh my God. He come answer my prayer. He come better my life. Now I get to walking home. Are you ready to celebrate? Are you ready to jubilate? Everybody, close up. You come to celebrate.